This lesson will be on proving trig identities. These identities may almost look like formulas, but let's just talk about what's going on. And let me just write down the first example I'm going to do as a way of starting to explain what we're talking about. In a few minutes, I'm going to work out this problem. Secant squared of theta times cotangent of theta times cosine of theta equals cosecant of theta. This is an example of a trig identity, and our job is to prove that it's true. And proving that it's true means showing that the left side is the same as the right side, or conversely, that the right side is the same as the left side. So do not think of this like a equation where we're going to solve for something. This is very different than that. We're simply trying to say, hey, this left side is really the same thing as the right side. And we want to prove that. And normally, probably 80 to 90% of the time, the way we do that is we take one side or the other, not both sides, just one side, and then we start making changes, start doing some substituting, start doing some kinds of simplifying, and we try and take one side, and by performing these operations, we try and get it to look like the left side. That's typically what we do. Now, from my experience and working with trig students, proving trig identities seems to be pretty challenging, although it still surprises me a bit because once you follow the steps I give you, hopefully you can start to figure out most trig identities. Some of them can be very difficult, but I don't think in this class or on the test you'll have any of the difficult ones. It's maybe a little bit like story problems where the only way you really get better at proving trig identities is to actually start to do some. And then as you do some, and as you figure it out, and as you learn things to try, then you get better at it. Proving trig identities can be a lot of trial and error. You try something, it doesn't work, or it gets uglier, you stop and say, well, obviously that doesn't look like it was productive, so you go back and you think and you try something else. Now, in the examples I'm going to do, hopefully when I do them, whatever I do will hopefully work, although maybe we'll see. Maybe I'll try something and it doesn't work, then I'll have to go back also and think of another way. So here are a few keys that, once again, doesn't work for every single problem, but usually makes things better. And the first thing is you work on the complicated side. In other words, the side that has the most stuff. For example, this problem. On the left-hand side, I got a secant squared, a cotangent, a cosine. The right-hand side, all I have is a cosecant. I would say the right-hand side is pretty simple. It's just one trig function. The left-hand side, I have three trig functions. One of them is squared. The left-hand side is the more complicated side, and 95% of the time, this is the side I'm going to work on. So I'm going to take this left-hand side and start to do some stuff and see if I can get the left-hand side to somehow end up equaling the right-hand side. Now, the second step that I do most of the time, I find it helps. It may not always help, but a lot of times it's a good place to start. Change everything to sine and cosine. Usually I find that that helps me. So in a minute when I do this problem, I'm going to change secant squared, I'm going to change cotangent, and I'm going to change the cosecant. Now normally you don't want to work on both sides, but in this case I'm going to change the cosecant and then leave it, because then I have my target or my goal in mind, and it's going to be either a sine or a cosine. So that's the one reason why I'll go ahead and change this right-hand side. And then the third step is just according to what you have. You try some things. You might want to, maybe you have two fractions. You need to add them together. Maybe you can somehow factor. There's all kinds of things you can do, and the more you do these kinds of things, the better you get. So what I'm going to do now in this lesson, this is one of those lessons where really you learn by doing. So I'm going to just work through like maybe 5 or 6 examples and just talk through, when I look at it, what I see, what I do, and go from there. Now let me stress again, what you cannot do in these kinds of problems, you cannot, when we solve equations, one of the main things we do when we solve equations is we do some math operation to both sides. In the simplest case, if I was to solve this equation, if I want to solve for x, the first thing I would do is I would subtract 1 from both sides, right? Subtract 1 from both sides. And then I would subtract x from both sides. And as it turns out, now I've solved the equation. We are not doing that here. We are not going to do something to both sides of the equation. We're not going to do the same thing to both sides of the equation. We're going to work on each side independently. Independently. Did I spell that right? Anyways, you work on each side by itself. You don't move stuff from side to side. You don't multiply both sides by something. You don't divide both sides by something. You don't take the square root of both sides. None of the stuff that we always do when we solve equations is used here. This is very different. You just take one side and you do what you can to that one side by itself, and you see if you can get it to look like or equal the other side. All right, so those are some of the principles. Let's dive in, and as I do some of these examples, hopefully some of the things I've talked about will become even clearer. So I'm now going to go ahead, since I've made a mess here, let me rewrite this first identity that I want to try and prove. So I'm going to mainly work on the left-hand side, since it's the most complicated, and I'm going to try and get the left-hand side to end up equaling the right-hand side. However, I am going to make one change to the right-hand side. I always want everything to be in sines and cosines. So I'm going to go ahead and change cosecant to 1 over the sine of theta. Now the left-hand side, I'm going to do what I normally do. I want everything to be in sines or cosines. Secant squared of theta is related to cosine. Right? Secant squared of theta is the same thing as 1 over the cosine squared of theta. Cotangent is cosine theta over sine of theta. And then finally we have the cosine, which is fine. So now you just start looking at what might work, and then you see, well, I've got some fractions here, maybe some things cancel out. And then I say, well, look at this. I have cosine times cosine. So really I have cosine squared in the numerator, and over here I have cosine squared in the denominator. So you see, well, all those actually will cancel out. And then what am I left with on the left-hand side? 1 over sine of theta, which is what the right-hand side is. So really, I've now proven, basically, I've taken the left-hand side and I've shown that it equals the right-hand side. I've proven this identity. Let's do another one. How about cosine theta over 1 plus sine theta plus tangent at theta equals secant of theta. So once again, you take the side that's the most complicated. Here it's the left-hand side again. Now I'm going to try and do some stuff to the left-hand side and see if I can somehow make it look like the right-hand side. And just, once again, just to make it easy on me, I'm going to say, well, you know, the secant is actually 1 over the cosine. So really, as I'm working over here, in the back of my mind, I'm saying, you know, what can I do over here to get this left-hand side to equal 1 over cosine theta? Well, in this case, let me go ahead and get everything to sines and cosines. This first term here is already sines and cosines, so it does not need to change. The second term let's write as sine over cosine. So here's an example of, you say, well, what do I do next? Well, you don't know for sure what to do, but one of the things you learn, you sort of learn little things along the way that sometimes help you. One of the things you learn is that when you have two fractions here, it's like two rational expressions, you just combine them into one fraction. And sometimes, simply by making them one fraction, things get simpler, things cancel out, things happen. So let me go ahead and do that. Let me try and make some room here. Let me try and fold this paper so we can get a new piece of paper and keep on going here. So basically, the left-hand side, I'm trying to get it reduced down to 1 over the cosine of theta. Well, you know, whenever you add two fractions together, what has to be true? You have to have a common denominator. Although actually, so here's a perfect example. You know what? I should probably do that just to show you, because I don't think adding these two together is going to be the best way to solve this. But just to give an example of what happens, that was my first thought, and see, I went ahead and did it. I'm going to have to get a common denominator. So the common denominator, if I want to add these two fractions together, would be this. Now this also might work. I don't know. I see another way that I think might be better, but let's just do this, and maybe I'll hit a dead end, and that'd be a good example of what happens when you're trying to do these kinds of problems. So for this first fraction, I need to multiply the top and the bottom by cosine. So I'll end up having cosine squared of theta over cosine theta 1 plus sine of theta. And for the second fraction, I need to multiply the top and the bottom by 1 plus sine theta. So I'd have sine theta 1 plus sine theta over my common denominator. And now that these two fractions have the same denominator, let's add them together. So here's my common denominator. Cosine theta times 1 plus sine theta. Now in the top, and you know what I'm going to do? I'm going to go ahead and write cosine squared theta. I'm going to go and multiply out this parenthesis. So I'd write sine theta plus sine squared theta. Now let me stop. Now this is actually going to work. But let me stop and tell you one of the most, probably the most used substitution when you're doing trig identities. Let me go over here and write it. Sine squared theta plus cosine squared theta equals 1. This is the one that gets used all the time. Now it takes other forms. Sometimes in a problem, you might have 1 minus cosine squared theta, and you know that that's going to be the sine squared of theta. So sometimes you'll see this as you're trying to prove a trig identity, and you can just replace it with sine squared of theta. Why I'm saying that is because look what I've got here. I've got cosine squared theta plus sine squared of theta. Just to make it very clear, since I'm adding things, I can actually rearrange the order. Let me write sine squared of theta, and then I'm going to add to it the cosine squared theta, and then at the end, I'll put the sine of theta. Of course, my denominator has not changed. Now look here. What I've got are 2. This equals 1. So I replace this with 1 plus sine theta over cosine theta 1 plus sine theta. And then I realize if I think of the whole numerator as this parenthesis, these cancel out. And I'm left with 1 over cosine theta. And if I look way back to the beginning of my problem, that's what I was trying to. All right, let me do a couple more, and then we'll be done. So let me do a couple more, and then we'll be done. Are you in the 6 o'clock class? Are you teaching? Mm-hmm. Oh, can I take about another 10 minutes?
Mm-hmm.
With these things, we can create these little videos, so I'm trying to give a little. All right, thanks. I'm sure you love trig anyways.
Yeah.
Okay, so for the next one, let's prove this identity. Cosine theta over sine theta plus sine theta over 1 plus cosine theta, and that whole thing should equal cosecant of theta. All right, so let's try and see if we can figure this one out. What I'm going to do here, here's one trick you learn. I could probably add these together like I did the last time, but here's something else that sometimes works. When you have a denominator like this, a lot of times you can multiply top and bottom by the conjugate. Let me just do it. The conjugate means you have a binomial, there's two terms, and you're going to multiply by the conjugate, which means the same two terms, but all that happens is you change the sign in the middle. Of course, I have to multiply the top and the bottom by the same thing, so I don't actually change this fraction. Because what happens is, this is a little trick, because I'm just going to leave the numerator like this. If you FOIL these out and multiply these out, you know what you end up with? 1 minus cosine squared. Now this, you need to get to the point where right away when you see this, you say to yourself right away, that equals sine squared of theta. You just need to know that. So I'm going to substitute sine squared of theta for this. So sine theta 1 minus cosine theta over sine squared of theta. And now I notice that this sine and one of these cancels out. So now I have, you can see sometimes these problems take up almost the whole page. And you notice right away, it's nice, I actually have the same denominator here. So I can go and add these two together. And look what happens. Cosine plus 1 minus cosine. Hopefully you see that cosine minus cosine cancels out. I'm left with 1 over the sine of theta, which in this case is the same as cosecant of theta, and lo and behold, that's what I'm trying to prove it's equal to. So here's another little trick. Sometimes you can do, when you have something like this, you can multiply by the conjugate, and it helps you out. All right, one last problem. So once again, you just have to practice these. You get better by practicing. Let me do this last one. This is an example where you actually can do factoring to help you. Now I said most of the time you just work on one side and try and get it to equal the other side. But there are times when you can actually work on both sides and try and make them equal each other. But just remember, you have to work on both sides independently. You can't be moving stuff back and forth from side to side. So here actually is a pretty messy looking problem. And it's not even obvious. Probably some people might want to start working on the right hand side, but actually I'm going to work on the left hand side because I see something I can do in the left hand side. I can sort of factor. I don't know if it's going to work. Once again, a lot of times this is just trial and error. So I'm going to work on the left hand side, and I'm going to, you notice in the bottom I have sine x minus sine squared x. I'm just going to factor out sine of x and end up with 1 minus sine of x. And then what I'm going to do is what I did on the last problem. When I have 1 minus sine of x, sometimes it helps if you multiply top and the bottom by the conjugate. So then I end up with 1 plus sine x in the top. And in the bottom, I'm going to have the sine x here. And once again, when you multiply these conjugates, if you FOIL it out, you end up with 1 minus sine squared x. And then right away, you should be saying to yourself, 1 minus sine squared x actually equals cosine squared x. So let's replace that sine x with cosine squared x. And then actually, if I stop here and look, I've actually come up with what is on the right-hand side. So those are some examples of trig identities. Sometimes it's trial and error. The more you do them, the better you get. But it's just a part of trig. So that's trig identities.